today's talk is going to be on the first two parts here. So the equity derivative pricing, which I worked on primarily, and the fixed income product pricing, which was Ryan Smith, and he will give the second part of the talk. So what is equity derivatives? What are derivatives, period? It's a financial instrument that derives its value from some other instrument, usually a more fundamental instrument like a stock or a bond or a currency or a commodity. The most fundamental unit of financial derivatives is probably the type of derivative, that is call or put. Calls have a positive correlation with the asset price, with the underlying asset price, and puts negative correlation. So financial derivative is an umbrella function for an interface to a library, a standalone library that connects to Mathematica, the Mathematica kernel, via library link, which is also a new feature in Mathematica 8. It allows you to connect pretty much arbitrary numerical or symbolic libraries to Mathematica. And the library that we've designed for financial derivative is a numerical library of solvers for many different derivative types. Broadly, the derivatives are split into vanilla and exotic options, or contracts. Vanillas being the options that you've heard about, like calls and puts, usually traded on open market. And exotics sometimes are also traded on the open market, sometimes not. And there are many more of them than there are of the vanilla types. But vanillas, broadly, they represent a much bigger portion of the market. So I think one of the advantages, and something that we've tried to really focus on in designing this the interface for this function, is to have it as unified as possible. So you have a single function, and you have a very typical way to enter parameters into the function. The first argument is the contract specification. And in this case, you see American call, which is actually not a complete specification. So it defaults to a vanilla option when the contract type isn't specified. So typically, the specification consists of three parts: the contract type, the exercise type, and the option type. So if the first part is omitted, then it's assumed to be vanilla. American is the exercise type, and it's a contract, so there are two sides to the contract. You are the holder of the option, having purchased it, and the other party is whoever wrote the option. And what exercise means is to present this contract for payment to the party that wrote it. So you can do that at any time with an American option, and with a European option, it has to be deferred to the expiration time. Finally, call or put specifies the contract type. Probably everybody in the room knows what that means. So the next argument is the contract parameter list. You can see that both of the next two arguments are lists of rules. And this is just really intuitive, and if you've used Mathematica, or even if you haven't, it's easy enough to understand. It's just a simple map. So the contract parameter specification just lists parameters that are specific to that contract. Sometimes there are, a vanilla contract has very few of them, just the expiration and the strike price. But for some other contract types, there are many more. Next to last is the ambient parameter specification, which are all parameters which are not dependent on the contract type. So for example, the current price of the asset, the dividend, they're not negotiated in the contract, but nevertheless have to be specified in order for you to be able to value the contract. And the last argument are the return parameters. In this case, I've specified value, which is the default return parameter. So if you don't specify anything as the fourth argument, then it's just returns the value of the contract. And the second one is critical value. And this is applicable to American options only. And basically, the critical value is the value at which the holder of the option becomes indifferent to either holding or exercising it. So it's usually, the option has to obviously be in the money in order for that to happen. And most frequently, it has to be deeply in the money. So just to emphasize the unified structure that we've designed here, it's very easy to start using this function. So let's say you don't even know what kind of contract you want to value. You just type in financial derivative. And in this case, I've filtered for just the American options that we support. And you select any one of them, enter it as the first argument to financial derivative, omitting the other arguments. And it will give you the set of arguments or the set of parameters that you need to input in order to be able to evaluate the contract, to price it. One other feature that we also introduced here is the ability to do some elementary date manipulation, date arithmetic. So in this case, I specify the contract as having an expiration in one time unit, making sure to specify all of the rates, like the dividend or the interest rate, in that same time unit. So the denominator in the rates is whatever the unit of time that I specified in the expiration. So for example, if it expires in 1 year, then volatility, interest rate, dividends are also specified as annual rates. But you can just as well specify it in date form. So you just say, expiration is on a certain date, and you also specify today's date, or some date in the past or the future. This is the list of inputs that are supported. So value and critical value we've already discussed, and the next 5 are the customary Greeks that you can also compute just by specifying them in that list of return parameters. And implied volatility is, sort of the flip side of that. If you have the value of a contract and you know the values of all of the parameters that went into valuing that contract, except for volatility, you can calculate the volatility that would have gotten you to that value. That only works for certain option types, primarily the vanillas. So in some cases, options can be valued by an analytical scheme, in which case there are not many numerical parameters to specify. But in others, you need to evaluate the contract numerically. So there is not an analytic formula for the contract price. So you have to just get down and dirty and actually do the calculation, evaluate the differential equation. So in that case, we allow you to specify the parameters that affect the accuracy of that calculation. So this is this little example shows the critical value surface as a function of the time left until expiration. And you can see here that I've specified the grid size that I used in order to evaluate the critical values at the different expiration times. And that grid size is actually more fine grid than would be the default grid. The critical value and the value are already converged at the default grid. However, for presentations or something like that, you may need a better looking graphic, so this is a way to obtain that. Here's another example where I'm specifying the method of solution, and I'm also specifying, which is the binomial tree method, and I'm also specifying the number of steps or nodes, so you can do that. Okay, so let's, I've prepared a few sort of applied examples. Basically, this first example, I'm plotting, like I said, we are capable of, the function is capable of returning the various Greeks. So if you consider the value of the option as a kind of function of the underlying price, so the dependent variable where the underlying price is the independent variable, then you can approximate this function by using just various polynomials, first order and second order in this case. And because we have the Greeks, which are the partial derivatives of the value with respect to the underlying price, you can do this approximation. So the function is expanded around about the value underlying price equals 50, And you can see that the linear approximation is somewhat good and gets worse as the farther away you go, and the quadratic approximation is better. Here's another example, sort of another way to state the same thing, which is a hedge table for the same option. Here's another example. So a short position on an asset is a position which is a diametric opposite of a long position, as the name suggests. So as the price of the asset goes up, a short position loses value, just as if the price of the asset goes up, a long position gains in value. So it has just the negative slope of whatever the long position has. So what I'm illustrating here is that some combination of two options, in this case, the purchase of a put option and the sale of a call option, is nearly identical to establishing a short position in the stock. And it's also cheaper to do so. The next example, I took it out of the documentation page for FinancialDerivative. And it's a way to use the internals of FinancialDerivative to illustrate really quite an interesting, or sort of intuitive concept, but nevertheless it's a simple way to illustrate something, which is the spread of returns as a function of the volatility of the portfolio. So I'm using here the solvers for the rainbow options, which are basket options, options on multiple underlying assets. And the independent variable is volatility. And I'm using the same starting price for each of the assets. And I'm basically seeing what will be the rainbow option. Its value is the value of the best or the worst performing asset, depending on the contract type, at the time of expiration. So in this case, you can see that as the average volatility is increased, the spread in returns between the best and the worst performing asset becomes larger. Finally, this example is a little bit even more applied. I took a bunch of data from a website which gives quotes for S&P 500, and I computed sort of my own volatility index. So the typical volatility index, it's called VIX, is computed based on some properties of the S&P 500 index. And this is shown in red, the VIX. And the surface itself is the theoretical volatility surface, just taken from the returns on the S&P 500 for the past year. And the y-axis is the deviation from the actual daily returns. So for example, if a return on a particular day was 5% above what it actually was, it would have caused the volatility, the annual volatility to go up for the entire year. So this is why you have these topographical lines mainly concentrated on the sides. And the green line is what I computed by taking snapshots of the entire market for S&P 500 index options, computing the average implied volatility for that basket of options, and plotting it, along this line. So because intraday there is some movement between the prices, you see that it doesn't lie on this 1.00 line, but nevertheless, you can see that it's actually, if you look at it like this, it tracks the theoretical volatility surface a little bit more closely than the VIX does.